Okay. Let's go for the De Moivre theorem.
Doctor, can you share your screen?
Yeah, sure. Sorry about that. So the De Moivre theorem What's the De Moivre theorem talking about? It's talking about the end root of any complex number, right? So any complex number z equal to x plus I, right? So how we can get the root square or the cubic root or etc. So this is exactly, I know the root square is z to the power half. The cubic root is 1 over 3. Okay, so I can write this one as z over 1 over n. Again, we said once we have a power, we cannot deal with the Cartesian form. We agree about this one last time, right? Okay, so what you are going to do, yes, I hear you. I have to change this one into polar form. Or it will be better if you go for Euler form. Do you remember this one? Yes. R e to the I theta. Okay. Yes, I know. What's R? Root square of x squared plus y squared. What's theta? As we agree, tan inverse y over x, but you have to make sure where is your zs, right? Is it in first quadrant or second quadrant or third quadrant or fourth quadrant, right? Because theta will be negative here and negative here. Theta will be positive here and positive here from 0 to pi, because I'm going to anti-clockwise. If I go with the clockwise from 0 to minus. We agree about all of these ones. Okay. Now, De Moivre says, no problem. Instead of z, you write r e to the I theta. And you bought 1, 1 over n, right? That's fine. Now, yes, the power with this one will be easy. So you will have r 1 to the power 1 over n e to the I theta times 1 over n. Okay. Okay, this equal to what? Let's change the color. R to the 1 over n e to the I, yes, theta over n. Okay. I know if I have the polar form or the polar form, z will equal to r open bracket cosine theta plus I sine theta. If I add to theta any period for, because I know sine and cosine are periodic function with a period 2 pi. So if I add 2 pi to theta, I will have no problem. If I add 4 pi to theta, I have no problem. If I have add 6 pi to theta, I will have the same value because I have a complete period. Okay, so instead of theta, I can replace theta by theta plus 2 pi k. Yes, this is the point. I have to explain it to you because I'm going to change theta by theta plus 2 pi k. Good. So I have theta plus 2 pi k over n. How you can write this one? Yes, I can write this one as R1 over n. This is the n root. Set. Open bracket, cosine theta plus 2 pi k over n plus, no need for this one. Okay. Plus I sine theta plus 2 pi k over n. What's k? As I said, if I put k equal to 0, I have the principal value or the original value or the first one. If I put k equal to 1, I add 1 period. If I put k equal to, I put etc. Is it infinite? No, it is not infinite. And up to k less than n or equal n minus 1. Okay, so I will write this one in different color just to not to have any confusion. Okay. Okay, shall we take a screenshot and go to the example? Let's go for the example. Find the cubic root of 1. Okay, you said it is 1. How it comes is 1. 1 is one of them, but you should have 3 roots. Okay, because I'm dealing with 1 as a complex number, right? Yes, I can write it like this if you don't mind. 1 plus 0i. Yes. Now it is a complex number. That's no problem because real number is a part of subset of the complex number. How to do this one? Using the De Moivre theorem. Okay. First, I should have r. R is the root square of 1 square plus 0 square. So it is 1. Okay. What about theta? It is tan minus 1. Y is 0 over 1, which is 0, right? Once I have r and theta using De Moivre theorem, okay, I have to write it down. N z equal to r1 to the n. This is why I got r and theta before I start. Cosine theta plus 2 pi k over n plus I sine theta plus 2 pi k over n, and k equal to 0, 1, 2, 3, 2, and so on. Okay. Okay, this is information you need to solve this one. and I have the component term. Okay, so the cubic root of 1 equal to, yes, 1 to the 1 over 3 open bracket cosine 0 plus 2 by k over n, which is 3, plus I sine 0 plus 2 by k over 3. Remember, k equal to 0 and 1 and 2, because n is 3, so I have to stop 1 before the 3. Now, let's have the first one. Okay, k equal to 0 give you what? I call it omega 1, the first root. So I have 1. Why I put this 1? Because it is real number, right? It's not a complex number. Cosine 2, I put k equal to 0, so I have cosine 0. What is a cosine 0? Yes, I hear you. 1. Sine 0 is 1. So this is the first one. Put k equal to 1. I will have W2. When you put k equal to 1, it means cosine 2 pi over 3. What is cosine 2 pi over 3?
Minus half.
Minus half, right?
Yes.
What about sine 2 pi over 3?
جذر 3 على 2.
Root square 3 over 2, right?
Yes.
Now let's go for the third one. K equal to 2. If you ask me without thinking, I will have the conjugate of this one. Is it okay? So it will be minus half plus root square 3 over 2i. Is it? Hello?
قلت لها نحسب ساين باي 4 باي على 3 صح؟
Yes, sine 4 pi over 3, yes.
ناقص جذر 3 على 2.
Yes. This is what I said. You have to remember 4 pi over 3 will be in which quadrant to make sure your sign positive or negative. Catch it? Don't trust your calculator in this case. And you have a reality saying any complex number, if it is a root, its conjugate will be a root as well, right? So this is the root of 1, okay? Let's multiply omega 1 times omega 2, okay? If you multiply, sometimes they don't call it down script, they call it here, right? And sometimes they call it here, right? But I prefer to call it subindex. If you called omega 2 by omega 3, what do you have? You have minus half minus root square 3 over 2 times minus half plus root square 3 over 2. What do you have? I have 1 over minus half over 2 squared, because this is square difference, right? Oh, sorry, I missed the I. Sorry about that. Okay, so minus half square minus I root square 3 over 2 square. So I have 1 over 4 minus I square 3 over 4, right? I square is minus 1, right? I know this is minus 1. So I have 1 over 4 plus 3 over 4 equal to what?
1.
Equal to 1. Which one? This one. This is omega 1. Okay? Fine?
Fine, Doctor.
Okay, so you can call you have a circle of the roots. This is omega 1, okay, omega 2, and this is omega 3. If you multiply it, you have omega 1, right? So you have, this is the 3 roots of 1. Let's have a different example with genuine complex number. Let's have a square screenshot for this one.
Doctor, what's omega?
What?
What's omega, the W? Can you just give a
Here it
brief
is.
explanation?
Here it is. Here it is.
Yeah, I saw it, but يعني
This is the
what's
roots.
its
The
شو
roots,
بتعمل يعني؟
just the name of the root.
Okay.
I call it any name. Instead of saying minus half plus root square 3 over 2i, I call it omega 3, right? Okay. And the main point, when you multiply the other two roots, it gives you the third one, right?
Yeah.
Okay. Now, let's have an example with the genuine complex number. Find the cubic root of I. Yes. How to solve this one? Before I start, without thinking about R and theta, I is here, right? Z is equal to I. So I is here. So I know R equal to 1 and theta equal to what? Pi over 2. Why I need to go through the formulas, and I know how to represent the complex number in Cartesian coordinate. Okay? So straightforward, R equal to 1, theta equal to pi over 2. Using the Moivre theorem, straightforward. If you don't like to write the formula, it is 1 over 3, open bracket, cosine theta is pi over 2 plus 2 pi k over n plus I sine pi over 2 plus 2 pi k over 3, and k equal to 0, 1, and 2. Let's have one by one. K equal to 0. So what do you have? You have 1 to the power, this is 1 as a real number, right? So you have what? Cosine pi over 2 over 3 plus I sine pi over 2 over 3. So what do you have? What is the cosine pi over 6?
Root square of 3 over 2.
So, and this one's a sine? Half? Is it? Okay, what about if I have, I call it Z1, the first root. If I get k equal to 1, so I have the second root, I call it Z2. So what do you have? You have cosine, you have k equal to 1, so you have pi over 2 plus 2 pi over 3, sorry, plus I sine pi over 2 plus 2 pi over 3. Okay, so what do you have?
الكوزين minus the root square of 3 over 2 minus the 2.
Okay, now let's go for k equal to 1, sorry, 3, sorry. I will write this one in a small way, just to have a space. Okay, Z3. You have cosine pi over 2 plus 4 pi over 3 plus I sine pi over 2 plus 4 pi over 3. So what do you have?
الكوزين صفر.
Sorry?
الكوزين صفر.
0, okay. And
الساين minus 1.
minus?
أيوه.
So the result will be what, Abdullah? Minus I?
Yes.
This is, you said this is 0, right?
هيك طلعت معي.
And this one?
minus 1.
Minus 1. So you have minus I. Okay. Now you can take a screenshot and have another example to be more aware with using our De Moivre theorem. Okay, let's go for example 3. Fine. Let's have something different from the cubic roots. 1 plus I. Also, I can have this z equal to 1 plus I is x is 1, right? X is 1. And also y is 1. So this is my z here, right? And I call it 1 and 1. So what is the angle here? Yes, I know theta equal to what? Pi over 4. Okay. What's r? R is the root square of 2. Okay. So without thinking and without going this road, I go for the solution by saying r equal to the root square of 1 square plus 1 square, if you like to do it in details. And theta will equal to tan inverse 1 over 1, which is pi over 4. Okay. Now I'm ready for the formula. Okay. Okay, I'll go for it. R, oh sorry, R is what? Yeah, root square 2 to the power 1 over 4 open bracket cosine pi over 4 plus 2 pi k over 4 plus I sine pi over 4 plus 2 pi k over 4 and k equal to 0, 1, 2, and 3 because n is 4. Okay, now let's go for k equal to 0 and we get z1 equal to k equal to 1, give me z equal to, but k equal to and give me z3, the third root, the last root when k equal to 3, z3 equal to. You just substitute by k equal to 0 and you have to get the result down here. Okay. The next example, I will give it to you just to revise the properties of the magnitude and the argument of the complex number. Scan this one. Okay. Now, let's have, this is our example was example 3, okay, it's example 4. Find, okay, the third root of 1 plus I over 1 minus I. Okay, that's good. Okay, so I have 2z in this case. 1 plus I know it is 1 and 1. And 1 minus I is this one. Okay, so I know the magnitude of 1 plus I equal to root square 2. And the magnitude of 1 minus I is also root square 2. The magnitude of the division 1 over 1 plus I over 1 minus I is exactly the magnitude of 1 plus I over the magnitude of 1 minus I. So it will be root square 2 over root square 2, it will be 1. And instead of just multiplying by the conjugate and have it as a complex number, why? It's better to use the properties. Also, you have the arc of 1 plus I is pi over 4. And also you have the arc of 1 minus I is what? Yes, it is minus pi over 4 because it is in the anti-clockwise. But this one is positive because it is with clockwise here. Okay, but this one anti-clockwise. So it is minus pi over 4. What about the arc of the division? The arc of 1 plus I over 1 minus I is exactly like the arc of the numerator minus the arc of the denominator. So what do you have here? Pi over 4. I'm sorry, minus pi over 4. You have minus minus, so you have plus. So you have pi over 4 plus pi over 4, which is pi over 2. Yes, I know this is the r and this is the theta. Yes, this is my r and this is my theta. Okay. Once you have r and theta, go to the formula of the Morpher and find it. Okay. Now we scan this one to go to the next one. Now I have the first root, or the root in general, is what? R to the 1 over n, open bracket, cosine theta plus 2 by k over n, plus I sine theta plus 2 by k over n. Okay, and k equal to 0, 1, 2. Okay. This is a general form. What about mine? Yes, I bought k equal to 0. Okay, I will have z1, the first root. What's r? Yes, again, r is 1 and theta is pi over 2. So I have 1 to the power 1 over 3, open bracket, cosine. Theta is what? Yes, pi over 2. Pi over 2 minus, sorry, pi over 2 plus 2 pi. Yes, I have k equal to 0, sorry, over 3 plus I sine pi over 2 over 3. Okay. So z1 equal to what? I will leave it for you. Now I got k equal to 1. So I have the second root. This is 1, so no need to worry about it. Okay. And you have cosine pi over 2 plus 2 pi over 3 plus I sine pi over 2 plus 2 pi over 3. And you get the second root. The last one. This is 1. Yes, k equal to 2, it means I have 4 pi here. Yes, you get this one. This is how to find the roots when you have a rational complex number like this one. Yes, it is better to use a formula for the arg of the division. Okay, let's have a scan and go for example when we have a multiplication, right? Example 1, this one, 5. Find the fifth root of 1 plus I times 1 minus I. Yes, I will catch the properties of the arc. I know 1 plus I, the magnitude of 1 plus I, 0 squared, 1 squared again, 1 squared again. I'm just repeating just to be familiar with the formulas. Okay, and I know the arc of 1 plus I is tan inverse 1 over 1, which is pi over 4. I can do this one without thinking. If I go for 1 plus I, this is 1 and 1. So I know that theta is pi over 2 and the square of 2 square 2, and this is pi over 4. Okay. Also, I can go for the other one, 1 minus I, 1 square plus 1 square, 2. And the arc 1 minus I, also by graphing 1 minus I is 1, 1 minus 1. So I have the angle here is negative because I'm anti-clockwise, so it is minus pi over 4. Okay. Okay. Now, if I go for the arch, the magnitude of 1 plus I times 1 minus I, and this is my R, it will be the magnitude of 1 plus I times the magnitude of 1 minus I, which is root square 2 times root square 2 equal to 2. Okay. What about theta? Theta is the arch of 1 plus I times 1 minus I. It is exactly like the arch of 1 plus I plus arch 1 minus I. So my theta will equal to pi over 4, yep, plus minus pi over 4, so I will have 0. Okay. Now I know the cubic root, the fifth root of 1 plus I times 1 minus I, okay, will equal to R. What's R? Yes, it is 2 to the power 1 over 5, open bracket, cosine, theta is 0 plus 2 by k over 5 plus I sine 0 plus 2 by k over 5 with k equal to 0, 1, 2, 3, 4, and I will leave you to find the Z1 and Z2 up to Z4, Z5, right? Some people, they call it Z0, Z1 and to Z4, okay, because Z0 is the principal value. Now I go through the De Moivre theorem, and you know how to find the complex roots of a real number when it is considered as a complex number. And then I have only imaginary complex number, and I get the root. Also, if I have a complex, genuine complex number with a real part and an imaginary part, and then I go how to find the roots if I have a division of two complex number or a multiplication without going through the division and the multiplication. Okay, using the properties of the magnitude and the arch. Okay, this is what I would like to say for today. I will stop recording and I'll give you some example and try to solve it together, inshallah.